the group 2 in the periodic table, and they always end in 2 electrons. If you look at the electronic configuration, beryllium, magnesium, if you go down the group, you see the end in 2 electrons. However, the one shell increases, like previously we had for beryllium we had just one full shell, and then another one which had only 2 electrons in its outer shell. But as we go down the group, what we see is that for magnesium, if I draw for magnesium, we do have one shell, one full shell, we have another full shell, and we have another full shell. Sorry. So we have one full shell. First one can contain 2 electrons, and the other one 8. So this one shall contain 8 electrons, and the outer electron that is it contains 2 electrons. So down the group, the number of shell keeps on increasing, and at last we have only 2 electrons at the outer shell. So what happens is uh, group 2 elements or group 2 metals, it's easier to lose 2 electrons rather than gaining full octet. Like they want to become stable, right? So they lose 2 electrons to become positive metal ions, and that's how they usually react. So down the group, the reactivity increases. If you go down the group from all the way to from barium, magnesium, calcium to radium, the reactivity would increase. And why is that? So if you look at the trend of the number of shell increasing, what we see is that the distance from the nucleus to the outer electrons, as the shell increase, the distance also increases, and so does the nuclear force decreases between the outer electrons and the nucleus. So they are less attracted to the from the positive. These electrons are negative charge and these are positive, so the attraction decreases and they're more likely to leave the electrons, the outer shell. Thus the reaction down the group increases. So moving on, so they're generally shiny white metals with relatively low densities and melting points. So it's their property, the physical property. Moving on, we have the melting points. So what we see is the melting points don't have any general trend, but they do decrease. We see them decreasing. Now, why is that? Like, if you look at the other elements, for instance, the like we have seen that increasing where the shell number increases or where the uh, number of electrons keep on increasing, we see that the melting point usually increases for like chlorine, and then we have bromine. So as their shell length increases and their electron increases, we see the melting point increase. So why isn't it the case here? So that shouldn't be the case here because they do not have covalent bonds, and they rather have metallic bonds. So that's no van der Waals force is working here. So that was the case for van der Waals force only, about the electron being more or less. But what happens here is that the melting point decreases down the group because, like, uh, so let's look at the first element. So for beryllium, if you look that we have the cations are very small, and they are very close together. The minus charge, I mean the delocalized electron, and the positive the positive charge. So as they are smaller, bonds are stronger, the ionic bonds. But if we go down the group, let's say we go towards radium. So the more down we go, we see that we have more and more shells, and so so the what happens is that the positive ions get as they get bigger, they are like so positive metals ions get bigger down the groups, and so there is less ionic bond. I hope you understand, because if you see that if the molecule is smaller, I mean if the ions are smaller, so more of them are being exposed to the electrons. I mean, and if the ions are bigger, less of it is being exposed. So there is more atoms, positive and negative ion interaction when they're smaller, and when they're bigger, we see the interaction is less. So if there is less interaction, what happens is uh, the attraction won't work so well. So the melting point down the group decreases, and that's how the melting point and the boiling point thing works. So down the group, the general trend is that the melting point decreases. Moving on, we have the trend in ionic radius. So as we go down the group, the size of the atoms increases. So down the group, what happens is the size of the atom increases. So we know why, because the number of shell increases down the group. Like as we go down, more and more shell are being added. So this is beryllium, and this is magnesium, and this is something. So this keeps on increasing. So that's what makes the ionic radius bigger down the group. And it's because the repulsion between electron increases. Like as you can see, repulsion between electron increases because there are more of the electrons here, and which outweighs the increase in nuclear charge. So though the nuclear charge increases because the number of proton increase, like it must be equal to the number of electrons. Like if the number of electrons are increasing down the group, so the protons can also increase. So the nuclear force should increase as well because of the number of protons increasing. But what happens is the distance is uh, the the shielding effect and the repulsion between the electrons and the distance outweighs that. So that radius keeps on increasing, and the second thing is the ionization energy, the trend in ionization energy that we have to know. So the graph that we'll get if we try to draw the trend in ionization energy, that it decreases, like it starts with beryllium and it decreases on the way, and like the last one should be radium. So that's how the ionization energy curve is. So why is that? So as we go down the group, what happens is that even to the nuclear charge increases that I've talked about, that like down the group the number of electrons are increasing up to the protons. So even though the nuclear charge is increasing, the shielding effect is more. As the shell number increases, the number of electrons are increasing at a good rate. So firstly we have only two shells. Now down the group we are having more and more shells, and we are having more and more electrons. So the repulsion between the electrons, and then there is another shell. So there is more electrons here. So the repulsion that we get from these electrons, that is more, and the distance also increases. So the ionization energy, when we talk about the ionization energy, we will be talking about the last electron. So for the last electron, where the energy we have to give is decreasing down the road, because the electrons before, for instance, in beryllium, it was more closer to the nucleus in here. So the electron knocking off this electron was harder because it was very close to the nucleus and the nuclear charge was square. But let's say it's radium, but so the electron is far away and this knocking on this electron is much easier. So the nuclear emission energy, the energy used for knocking off the last electron, decreases rapidly. So in the next video we will look at the reactions of these two elements, and we will keep the video up to this. So goodbye.